So how do we measure speed and how do we measure the slope at a single point? These are both the same question in a way, where we're looking to finding the rate of change at an instant instead of over a window of time. That question in itself is somewhat of a paradox until we come to limits, which is the whole concept of this unit, and it's what underpins all of calculus. So it's like the most important thing we're actually going to learn all semester, because everything in calculus rests on top of the limit. What is the limit? We'll get there. First, we're going to motivate it with this question of how do we measure speed? So let's dive right in with an example. So the example I always start with is throwing a grapefruit off of a building. Let's make it the Empire State Building. So we're about 300 meters in the air, and we nudge off a grapefruit, and we want to know how fast is this thing falling at any given moment. It's an interesting question. But again, in that question lies the paradox. How can you have a speed if time is frozen, right? If we're just picking one instant in time. So it's somewhat of a challenge. It's a very challenging question. It eluded us for thousands of years. We only recently figured this out about 400 years ago. So how do we measure the speed? Well, let's drive at this problem as if we're trying to solve it, as if we don't have calculus, which you don't yet. So how fast is it falling after 5 seconds? So what do we know about this grapefruit? Well, we know it's subject to gravity. We haven't thrown it downwards. It's just kind of falling free fall. So we know that its displacement, s of t, is going to be governed by the acceleration due to gravity, 4.9 meters per second squared, times the square of time. So 4.9 t squared. This is like a free fall distance formula. So this is the distance it's traveling, not its height. So it's important to note. So that's going to be how far it's fallen at any moment in time, assuming it's obeying gravity. So how fast is it falling after 5 seconds is really asking how fast is that distance changing. So how do we measure the change in distance with respect to time? Well, we only have right now the average rate of change, where we say the change, which is represented by delta, over delta in s over the delta t. So the change in the speed over the change in time. We're talking about miles per hour, feet per second. Here we're talking meters per second. So that's the rate of the distance traveled or the speed at which it's falling. But here's where the issue comes in. We need a delta t, right? Delta t can't be 0. First of all, we can't divide by 0. And second of all, we need a window of time to compare how fast something's moving, right? We need 2 discrete points to say, well, move from here to here. So I'm just kind of beating this drum to highlight the nature of this problem, how fundamental it really has been and is. So let's go ahead and try to approximate the velocity. So if we approximate the function of velocity, we're going to say it's approximately delta s over delta t. So if we care about the moment t equals 5, let's drive at that. So how are we going to approximate it? Well, we could look at the values between 5 and 6 seconds based on our formula. All right, so the rate of change here would be s of 6 minus s of 5. We're just using the average rate of change formula here over 6 minus 5, right? End minus start of the dependent over end minus start of the independent. Might be a bit since you've seen that, but not if you did the review in the functions chapter. So what is s of 6 and s of 5? Well, I can actually pull up my table here. So in Desmos, which I highly encourage you to use, you can throw in the formula here, even in terms of t, that's fine, and then generate a table like we did here, and then you can enter your own values. So I wanted to see what's going on near, let's do s of 6 and s of 5. Oops. We don't need you. S of 5. So This is the distance it's traveled after 6 seconds, which makes sense. It's a little bit farther than after 5 seconds. And so to get that rate of change, you can actually just punch this in the formula mode. Divide this all over 6 minus 5, which is just 1. And so we get this is 53.9. Let's come back to our paper here. So this is 53.9. What are the units here? Well, it's the units of the top, which is meters, over the units of the bottom, which is seconds. So that's all meters per second. Okay. So now this is our approximation. But I'm going to say this is bad. Why is this bad? We used a full second of time to elapse before we measured the how far it's gone. So can we shrink up that time, given that we have the formula for how this thing falls pretty accurately? So let's instead look at, we'll zoom in a little bit on the window. Now a better look, because remember we're looking around t equals 5, that instant in time. So maybe let's look at 5.1 instead. And so we'll look at, the velocity is approximately this change in distance over change in time, which is s of 5.1 minus s of 5 over just 0.1 here, the difference between the two. And so if you go ahead and do that, and I'll do this in my calculator off screen, you can do it along with me, we get 49.49. All right, so that's considerably different than what we got before. This is still not great. Again, 1/10 of a second for something falling is still a considerable window of time. There's a gap in our information. So let's try our level best and just say a little bit better would be if we could, it looks like my iPad's delayed behind me a little bit. Sorry if that's confusing. See if we can fix that for the next video. But here, let's, try even better would be what? Try to get as close to the instant as we can between t equals 5 and t equals 5.001. And what do we see? S of 5.001 minus S of 5 over 0.001 is going to get us 49.0049 meters per second. Again, this is getting pretty good. And what we're seeing, if we keep getting closer and closer, zooming in further and further on t equals 5, we're going to see that this velocity is approaching 49 meters per second as t approaches 5. And so this arrow here means approaching. We're going to more rigorously define what approaching means later. But this is what we're seeing. It's getting closer and closer to 49 meters per second. Can we say that it is 49 meters per second? Yes and no. Right now, not really, but we can say with our best guess possible, this is how fast it's moving at that instant. So this is precisely the problem that's been worked on for thousands of years. And where it really comes from, I'll just tell you briefly, is what's called the tangent problem. You might remember this word from geometry, or maybe not, but what is the tangent problem? Well, the idea was, how can you find the slope? That's not a perfect line there. If I have a line L and a circle C, and I've got this point here, P, can I find the slope of the line that just touches that circle? That doesn't look like a circle, does it? That just touches the circle at point P. So it's a single point, so it just kind of kisses the curve and goes off. So we're finding the connection between things that are straight and things that are curved. It's actually a very difficult problem to do. We've only had approximations for so long. What's much easier to do is get the what's called the secant curve, or the secant line, where a line passes through 2 points, you can do this much easier. Let's call this P and Q. And this is our line L. So we can find this slope very easily. Why? Because we can measure the distance here and here. Here's my delta x, here's my delta y. Or for the example we just did, it was what? Delta s in the height and delta t for time. So this is the same exact problem. How can we shrink the difference between the 2 points of the secant line down to the tangent line? And so in the same way, you might be saying, well, this isn't a circle. This thing wasn't falling off a circle or traveling around. It's the same problem if you look at just some curve, any curve f, and we're looking for the slope of the tangent line here, the instantaneous speed at that point. That's a lot harder versus having some curve f, and let's say I've got some line that passes through 2 points. This is the secant, because it's got 2 points. This is the tangent. So what we're going to do with limits, and what the breakthrough was here, was the ability to rigorously define how you shrink that distance down to 0, thereby getting around the paradox of dividing by 0, right? Like we said up here, we want this to be as small as possible, but we can't divide by 0. It's like fundamental to mathematics. So how do we get around that? So that's where limits heads, okay? So for this video and this section, just wanted to motivate that we're coming at this from a measure of speed, but really this problem has always been, how do we connect things that are straight and things that are curved, right? So things that are continuous and things that are discrete in the moment. And so the connection between the geometric problem and applied problems, since we care about rates, and you've heard me say probably already that calculus is the mathematics of change. This is the connection between all these things and why calculus is so prevalent in so many different fields of mathematics, because of this specific problem and all the applications that emanate from that. So hope this is helpful. We'll see you in the class discussion. Have fun.